Okay, so this is going to be our second lecture on Kepler's laws. This is going to be a proof of Kepler's second law. So, this one's a bit quicker and easier. So remember, Kepler's second law is that the line that connects, an imaginary line that connects the Earth to the Sun, as the Earth is moving around the Sun, sweeps out an equal amount of area in an equal amount of time. So no matter where on the ellipse it is, if you measure that area over an equal amount of time, it should be the same. Okay, so sometimes this is called the law of areas. Okay, so, and just to give you a picture to go with this, if you've got an ellipse, an elliptical orbit, the Sun sitting at one focus, right? This is what we proved in the last lecture, is that the Sun sits at the focus of the ellipse. Then at some time, let's say at t1, the Earth may be here, and at some later time, t2, the Earth may have moved to this point, and the area swept out during that time, delta t, is going to be equal to the area swept out at some other part of the ellipse where an equal amount of time has passed. So on this more distant part of the orbit, you would be the Earth would be moving slower. So even though the time difference is the same, this would be the same delta t as that delta t. Because the Earth is moving slower out here, it sweeps out an equal amount of time, right? It's got a kind of a longer triangle that's skinnier versus a shorter triangle that's fatter. So let's prove that this is the case. So that what we're going to calculate here then is the area of the swept out territory there. Okay, so the way we're going to do that is consider a short time, and so that right now I was imagining a rather large chunk of time, delta t, but to prove this we're going to consider an infinitesimal short dt. So consider infinitesimal, that is very small change in time, dt. Okay, so during that amount of time, there will be a change in the angle, right? The angle that's swept out here is phi, so there's going to be some small change in the polar angle as this thing is moving around the ellipse. So in considering that small time and the small amount d phi of the movement, then it's basically covered an arc length. So the trajectory between the two points during the time dt covers an arc length of rho d phi. Okay, and the area of a wedge that has rho d phi on this side and radius rho is, or a small area that's swept out, a small piece of area dA that's swept out, is approximately equal to 1/2 rho times this arc length rho d phi. Now, and this is approximate, right? This is only true if these are infinitesimal changes, right? This is exactly true if this was actually a triangle with a flat side here, but this is only approximately true, or it's only exactly true if this is an infinitesimal change, right? If you make a tiny, tiny change here, then that's basically a flat arc length, and you can use this area of a triangle for your formula. So, all right, so that's the infinitesimal area swept out by the line. Then we can go ahead and use that to write down how the area, if you start considering how does that area change with time as, say, this line is sweeping, then it is the following. Okay, so it's dA divided by dt here, so that's going to be rho squared over 2 d phi, and then divided by dt, right? So that's basically, we have rho squared over 2 phi dot. That's how the area of a swept out by a line increases with time during one of these elliptical orbits. And then the key fact here, if you remember, due to conservation of angular momentum, the angular momentum of one of these orbits is a constant, and it's equal to the reduced mass times rho squared times phi dot, right? And this is a constant. That's the angular momentum. Okay, so then clearly this area is directly proportional to the angular momentum, which is a constant. So then our dA dt is just equal to L over 2 mu. Right? You take this thing and divide it by 2 mu. Or sorry, you take this thing and you divide it by 2 mu, you get that. So that rate of increase of area is a constant for an elliptical orbit like that of the Earth around the Sun. And then, just to be 100, that's probably clear already, but just to be 100% clear, if you want to talk about these finite chunks of area in equal time, then if you're considering a time interval, delta t, because this is a constant, you can do this, right? So for a time interval that's delta t, now this is not an infinitesimal time interval, this is a big time interval, the total area swept out is just going to be big A, which is dA dt times this delta t. And this is only possible in this case, remember, because this is a constant. If dA dt were changing with time, you can't do this without some kind of integral. Okay, so this is equal to L over 2 mu delta t. And if this delta t takes place at this part of the orbit, or at this part of the orbit, or this part of the orbit, doesn't matter. It's always going to be the same area swept out. And that's Kepler's second law.